All right. Hello, everyone. Today our thanks for coming to the meeting. Really appreciate it. Today our meeting is going to be on a paper that I made a presentation for a class. This class is CS 598 IoT Home Security. So it's security and privacy in home IoT devices. And the paper is a mouthful. It's discovering and understanding the security hazards in the interactions between IoT devices, mobile apps, and clouds on smart home platforms. This is based off a paper that I linked in the announcement screen, in the announcements page. It is a 2019 paper by Zhao et al. All right, so real quick announcements. Tracer Fire, I'm not sure if the registration is closed yet, but you can probably late register. You could reach out to us and we can probably reach out to the Sandia people and they can get it registered. Right after this, it's starting to warm up just a little bit. So I'm going to send out a when to meet for the spray paint social. Basically what that is we're going to go to the SIP yard, which is in Urbana, and there is just an alleyway where you can spray paint things. And we're going to do that. That'll be a really fun time. And then smiley face, because there's only 2 announcements right now, which is good. Real quick, the meeting flag is Internet of Funk. That's a 3 and a 0 in there, I think. Just do whatever I pasted into the chat. Just copy paste that from chat. And it should be in a dedicated spring 2022 meeting flags, IoT meeting flag. There it is. Thank you. All right. So let's get started. Real quick summary of this. Smart home platforms, so something like a General Electric or Feed Electric or something like that, or like even Alexa, have 3 entities that are interacting most of the time. There is the cloud infrastructure that does a lot of the computing. There's the devices themselves that are doing the actual action. And there's a management interface. Most often, the management interface is a mobile application. And these entities are going to interact with each other. So I could send a command from the mobile application and it will get processed on the cloud infrastructure, and then the cloud infrastructure will tell the device to do a thing. Or I send the information directly to the device itself. It really depends. But what's important is that this process, these interactions between the management infrastructure and the device, the management infrastructure and the cloud and the device all come with crazy security risks. And this paper explores those. So the novel contributions of this paper. Most of the other papers in IoT security focus on subsections of smart home platforms. So that's something like a smart vacuum or smart lights or something like that. Then this paper instead decided to study the platforms themselves and study them pretty holistically. So look at the whole platform. Second, existing platforms paid attention to the more traditional security issues, whereas this paper studied IoT-specific vulnerabilities that exist. And third, other papers define operations differently and just how entities interact with each other. This paper defines interactions as basically the inner operations between entities. So how the management device is interacting with the some other device. So just those are really the things to be conscious of before we go into this. And that's also their novel contributions to this. So real quick, some background. Smart home platforms. It's something that you can put into your house to make to provide a little bit of automation and convenience featuring with your house. That could be everything from a smart dishwasher to a smart fridge. I don't know who would ever buy a smart fridge, but it provides some amount of convenience and some amount of automation to your home life. Typically the cloud is the brain. It's going to provide the automation services themselves, as well as a fair amount of the computational power, because the IoT devices are just the muscle. They don't really have that much computational power. They're not going to be able to do that much because a lot of them are really small and just mostly equipped with a microcontroller. They will interact with the physical data and they could send data to the cloud. So that's something like your commands, if it's something like an Alexa, or sensor data, if it's a thermostat or a carbon monoxide detector. Then the mobile apps are also the brain, but kind of like the decision-making part of the brain, where you actually like send it commands and it will you tell it to do things and it'll instruct the rest of your brain to do the things. So then there's two types of devices, and this is really important for the rest of the paper. There's devices that get directly connected to the internet, and those are type 1 devices. And then there are devices that are connected to the internet through a hub device. More often, these devices are super small. So like a light bulb, it's small. It's not going to have the capacity to go directly to the internet. So it's going to go through a hub device. And that's type 2. So there's a lot of interactions here. This is the kind of the summary of all of the interaction process for an IoT device. It starts with device discovery, where you're kind of finding the stuff. Then Wi-Fi provisioning, you're going to let the stuff connect. Then the next 3 steps are really all part of like the association process. You're going to register it with the cloud, associate it with your specific account, and then log in to make sure only you can control that stuff. And then it's in use, which is, you're doing things with the stuff, the IoT devices. And then you're going to do like an unbinding or reset command, which removes it from your account, which is goodbye stuff. So device discovery, it starts with the device coming online. So that means you plug it in, you plug the light bulb in, you plug the TV on, you turn on your fridge. And then the user will, once the device comes on, more often than not, it's going to connect via a smart home platform. So it will like send out a broadcast signal that says, hey, I'm a unpaired smart device. You should pair with me. So then the user will add that device on the control application. So that's usually you open up the phone, go to add device, and it'll search for the broadcast pairing messages. So the app, the management interface, will connect with the device using a discovery message. Again, type 2 platforms, the ones that have to go through the hub device, have to go through the hub device to do this. They can't just connect directly with the phone. And then lastly, within the discovery process, the device will report basic information. So that's something like a MAC address, a model of the device, any of that stuff. Is anyone confused about like the device discovery process? I'm going to wait for like a minute if anyone has questions. I just want to say I broke the hanger taking this down. So, okay. All right. So step 2 is Wi-Fi provisioning. Basically, you're just going to share internet access with the device. Sometimes this means doing something as vulnerable as sharing the credentials in plain text. It could also mean you set the device temporarily to access point mode, so it can set up its own connection, or something called smart config, which I'm really not sure what that is. But it was just they talked it up in the paper. So yeah, then you got to make sure that the device is connecting to the same LAN as the app that you're doing the connections with. So if you have a 2G, 2.4 gigahertz and a 5 gigahertz Wi-Fi, you got to make sure the devices are on the same frequency or just on the same LAN. So the third step is device registration, where the device is given an identity. So for type 1, the device sends its information like its MAC address and stuff to the cloud, and the cloud will give it an identity. Whereas in type 2, the ID is hard coded, and the process is just skipped completely. So for type 1, the cloud will respond back with the device ID and also store that ID associated with that information. And then the device will write that ID to its memory, because again, it has the computational power to do that. So step 4 is device binding, and how that happens is the cloud will bind the device ID to the owner account, because it assumes that when you're registering, you're signing up under an account. So it takes that device ID and connects it to your account. For type 1, binding is sent by the mobile app, and type 2, it is sent to the account, and then the account makes the binding request to the cloud. Really interestingly here, and this might become a problem later, the cloud will unconditionally accept binding requests because of the assumption that the customer has physical access to the device, and therefore they have full control over the device itself, which is interesting. Then you're going to log in, and this is just pretty simple. The device uses its ID to log into the cloud, and then it establishes a connection. When the device loses connection, it will reconnect automatically. That's another interesting thing. And then once it's in use, it's going to just operate as intended. And then with an unbind, the device can be manual. It's usually manually unbound. For type 1, the cloud directly erases the binding info. And then for type 2, the command is sent from the cloud to the device to erase the binding information. So you can do it again. So you can add the device somewhere else. So that's if you're, say, selling the device or transferring it to a friend. So here's the state. This is a lot of stuff, but this whole process comes down to state transfer for the different processes here. So on the left is the cloud. In the middle is the app itself, I believe, and then on the right is the device. And here, it's a big process, and there's a lot of places where it can be attacked. I'm not going to go into this too much, but it's a state diagram, because once you're done, say, waiting for a device to register, you're going to move to a different state. And abusing those transitions is something that they tried to do in this paper. So here's their methods. They had some goal information that they wanted to get. There were 3 different kinds of information. There was public information, so that's something as easy as like the device model or something like that. Then there's guessable, which is maybe like a default password or like a simple password, like a PIN. Then there's hard-coded information, so that could be like device ID or like MAC address if that's hard-coded on. Then the threat model that they had to consider if they had physical access to the devices, and then they had to consider what information they were allowed to have as kind of like an assumption, like, oh, let's assume we have this information. And then the 2 things they assumed they had access to were identifying information, which is like what the device is, and then legitimacy information. So like they had the ability to see like keys and stuff. So their attack flow was pretty simple to understand. Step 1 was to decipher communications. So that was cloud app, device to cloud, and device to app communications. The most common way to do that was with a man-in-the-middle attack, which basically means between A and B, you inject yourself into the middle and become that middle target. So you can see any messages coming through. You can modify any messages coming through. You could usually decrypt the messages that are coming through. So it's a pretty powerful ability. And then you can once you can decipher those communications, you need to be able to understand those messages. So just because you've deciphered it and it's unencrypted and you can read it doesn't mean you have any idea what it means. So figuring out what the API calls mean, what any commands mean is the second step. And then the third step is the coolest, creating phantom devices, which is basically like creating a clone of that device and make it basically Burp Suite, but which is like it's a networking protocol. It's a networking proxy where every single time you send a packet out from your computer, Burp Suite will stop it and allow you to edit it before it actually gets sent off. So what a phantom device does is it allows an IoT device to behave like Burp Suite and stop right before it sends out any commands, so you can mess with them, which is really cool. So they used real quick. They used 5 devices. They used 5 whole platforms. They used SmartThings, and the website is linked there. You'll be able to get that if you're interested. Then they used Casa, Mihia, A-Link, and Joylink. Interestingly, Mihia and Joylink didn't even have websites. I could only find them through their Amazon catalogs, which was interesting. Okay, cool. So results, quick summary. They found 4 kinds of vulnerabilities. The first vulnerability was insufficient state guard. Basically, what that means is that they were able to use really weird requests to enter an invalid state. So that could have been like an in-between state or just something weird. The cloud often will just accept these requests because it doesn't have... IoT is kind of fundamentally broken because they didn't really think about security, because a lot of IoT is about getting it out as fast as possible and as cheaply as possible to beat the competition. So they didn't put in good state guard, so you can get into invalid or illegal states, and you can use that to do some of the other stuff. So the second kind of vulnerability was a result of the first one, and that's illegal state combination, which basically combines states to violate security assumptions. This abuses insufficient state guard, and it's required for the next 2 attacks, which were really the actual scary attacks. And examples of the illegal state combination are something like a synchronization attack or a race condition, which is something I can explain if anyone's confused. Does anyone, if you don't know what a race condition is, can you raise your hand and I can explain it? Otherwise, I'm going to move on. Anybody? Okay, cool. So just real quick, a race condition is basically when the timing, when 2 processes are running and the timing of one of these processes matters in the case of program security or program success. So a really great example of a race condition that I personally discovered was at CipherCon my freshman year of college, where in between it was a CTF and they rolled their own infrastructure for the CTF, which is a terrible idea. Don't do that. But in the time that you would send a flag out to the server and the flag would come back and say, this has been submitted, you can no longer submit it. You could submit the same flag again. And you could do that over and over and over and over and over again. And it could give you a multiplicative amount of points. And why that happened is because while the server had not marked that flag as solved for our account, you just keep submitting it and it would solve it faster. It would give us points faster than it marked it as solved in our inventory. Yeah, so it involves asynchronous locks. So something doesn't lock fast enough and it gets changed. That's basically what's going on with race conditions. It's an issue with multi-threading and parallelism. Yeah, no problem. So yeah, so illegal state combination is just abusing things like synchronization and race conditions to get that to happen. And then what results of that are 2 things. Unauthorized device login, which essentially allows you to connect to the account with a fake device, and then unauthorized device unbinding and basically hijacking a device altogether, which means you can just take over a device. So we're going to talk about all of these. Well, 2 of them, the last 2. So the exploitation result for substitution was really, really interesting. So that's the where did it go? That's weird. Okay, so anyway, so the substitution attack was the unauthorized device login. And what that basically means is you're going to obtain the legitimate information like the device ID, and then you're going to create a phantom device using that obtained information. And then lastly, you will substitute the real device for the phantom device and log in as a fake device, which can do some interesting stuff. Basically, to do that, you would sniff the device ID when the target binds the device, and then log into the phantom device without the target. Trudy is just the targets, without the target's credentials, and then have the device log in really rapidly to beat the other device. Because as I said in step 4, it would log in. If the device ever got logged out, it would rapidly log back in. And the issue with that is if it logs in, if two devices of the same ID log in, one device is just going to boot the other device off. So the trick they figured out was to just rapidly re-log in again and again and again to keep the actual device booted off. The implications of this are cool and scary. So privacy breaches, any commands meant to go to the actual device can go to the adversary. So say you have like, I don't know, smart lights, and I like smart lights, so I'm going to just use them as an example. So say you have smart lights and someone sets you have a phantom device, and that phantom device receives set it to party mode, right? Then maybe you can assume with reasonable confidence that, oh, it looks like a party or something of the party nature is going on in this location. Maybe I want to crash that or something like that. Then falsified data from the real device is intercepted by the adversary, which means for it to go to the app, it can be modified. So you have a man in the middle. And it's also really stealthy because there's really no way for the target to tell that their device has been attacked. Just because it's been substituted and there's a successful man in the middle. So how would they know? So then the other one was remote device hijacking, which is basically a deauthentication attack where you force a device to either remove itself from the network or remove itself from an account, and then hijack that device by re-registering that device to your account or binding it to your account. The consequences of this are that the adversary rebinds the device to their account so they can have control over that actual device, which if you need to do something for like 5 or 10 seconds can be really powerful. But it's not as stealthy because the target can very much notice the missing device. So then there's a few other security hazards like a remote denial of service. And how that worked is you would just boot the person off their own account and then they try and register it and then you'd boot them off again and they essentially just cannot use that device. Another thing was so funny that they did this. I'm not totally sure if they did this, but this was something they theorized. You can predict the device IDs of unsold devices and then take them over the second they get registered, which is pretty nuts. And then firmware theft. To reverse engineer these protocols and to attack this stuff, leaked firmware can allow for researchers to do this faster and do it better. And they figured out how to just dump code off of a lot of these IoT devices. So it was done successfully like thousands of times in this paper. It's worth a read. It's pretty neat. So here's some of the solutions they came up with. And then we're actually going to talk about what you all think might be some cool solutions to this problem. So cloud-free platforms can help a little bit, like Apple HomeKit, because it will stay locally, which means someone can't just mess with your stuff randomly from the internet. Another thing that you could do is a DIY IoT platform, which is like an open source platform or like security through obscurity, where you're going to avoid standard attacks that know how to use the standard platforms. That's a little bit of a risk there because I know you're using something open source, you might misconfigure it. It's much more on you to configure it correctly. And then some of the more technical solutions are strict authentication, comprehensive authorization, and just like some of the more traditional security stuff, as well as IoT specific stuff, which is enforcing valid state transfers only. So making sure that when the device is transferring and when it's changing stuff, when it's changing its state, it has to be valid. And then so some of the commonly asked questions, let's just skip. Next, so real quick, our next meetings are going to be Windows environments. And then for this Thursday, and that'll be really, really cool. We've been waiting to run that for forever. And then the Sunday seminar is going to be open. Right now it's UAE-CTF planning. If Aditya is able to, that would be awesome. That he could run a meeting on crypto math. Otherwise, we'll just plan UAE-CTF some more. All right, cool. Does anyone have any questions about this paper? I know it was a lot. I know I just put a lot of information on y'all. But it's, it's an academic paper. It's our Sunday seminar. So yeah. Otherwise, I'm going to stop the recording and we can just talk about this paper. Or at least I'll pause it. Any questions?